Hello, everyone. Welcome to our Deep Dive podcast, where today we'll be reviewing the paper Visual Programmability, a guide for code-as-thought in chart understanding. Are you ready to explore the future of chart reasoning with me?
Absolutely. This paper is quite a milestone in the field of vision language models, or VLMs. It tackles the challenge of chart understanding, which is a critical test for any AI's reasoning capabilities. Shall we start by discussing why chart understanding is so important?
Yes, that's a great place to begin. Chart understanding isn't just about reading numbers or recognizing bars and lines. It's about connecting low-level visual perception with high-level logical inference. In other words, it's a true test of an AI's ability to reason across modalities.
Exactly. And as the paper points out, even state-of-the-art VLMs struggle with complex, real-world charts. They might do well on simple, structured charts, but their performance drops sharply when faced with in-the-wild visualizations. Why do you think that is?
The authors argue that the problem isn't a lack of model capability, but rather strategic rigidity. Most existing approaches fall into two camps. Either they rely on external tools, which are limited by their predefined functions, or they fine-tune specialist models that use a single reasoning strategy, like text-based chain of thought or code-based reasoning.
That's right, and both approaches have their drawbacks. Tool-based models are brittle. They can't handle tasks outside their toolkit. Specialist models, on the other hand, lack flexibility. They're great at one thing, but can't generalize to new types of charts or questions.
So, the paper introduces a new concept: visual programmability. This is a learnable, task-dependent property that tells the model whether a chart question pair is best solved through programmatic reasoning or direct visual analysis. It's a shift from how to reason to when to use which reasoning strategy.
That's a key insight. The authors implement this idea in an adaptive framework, where the VLM learns to choose between a code-as-thought pathway and a direct visual reasoning pathway. The selection policy is trained using reinforcement learning, with a novel dual reward system.
Let's break that down. The dual reward system combines a data accuracy reward, which grounds the model in facts and prevents numerical hallucination, with a decision reward, which teaches the model when to use each strategy. This prevents the model from defaulting to a single reasoning mode.
That's crucial. Without the decision reward, the model might always pick the safe strategy, leading to what's called mode collapse. But with both rewards, the model learns to adapt its reasoning style to the task at hand.
The experiments in the paper are quite comprehensive. The authors used the Quen 2.5-VL model and evaluated across 4 benchmarks: ChartX, ChartBench, ChartQA, and ChartXIV. Each benchmark represents a different level of visual programmability.
For example, ChartX is full of highly structured charts, perfect for code-based reasoning. ChartXIV, on the other hand, contains complex scientific charts, where code-based reasoning often fails. The adaptive model learns to use code where it's advantageous and avoid it where it's not.
The results are impressive. The adaptive model outperforms both pure visual baselines and rigid code-based methods. On high programmability benchmarks, it uses code-based reasoning over 60% of the time. On low programmability benchmarks, it drops code usage to less than 10%.
That's a clear sign of strategic intelligence. The model isn't just good at reasoning, it's good at choosing how to reason. That's a big step forward for AI.
Let's talk about the concept of visual programmability in more detail. It's not a binary property. Some charts are highly programmable. Think standard bar or line charts with clear data points. Others, like complex scientific visualizations, have low programmability.
And it's not just about the chart itself. The nature of the question matters too. For example, a chart might be programmable for a counting task, but not for extracting a precise value from a logarithmic scale. The model needs to assess both the chart and the question to decide on the best strategy.
To train the model, the authors developed a framework for annotating data with visual programmability labels. This provides the necessary signal for the model to learn adaptive reasoning.
The adaptive reasoning mechanism is formulated as a policy learning problem. Given a chart image and a question, the model first selects a strategy token, either code or direct, and then generates the corresponding reasoning and answer.
If it chooses code, it generates code to parse the chart and compute the answer. If it chooses direct, it uses natural language chain-of-thought reasoning based on visual perception.
The training uses Group Relative Policy Optimization, or GRPO, a policy gradient algorithm that's efficient for tasks with verifiable, sparse rewards. The reward function is a weighted sum of 4 components: accuracy, decision, data accuracy, and format.
The accuracy reward is binary 1.0 for a correct answer, 0.0 for an incorrect one. The decision reward incentivizes selecting the correct strategy based on the chart's visual programmability. The data accuracy reward ensures the code-generated data matches the ground truth. The format reward enforces correct output structure.
This multifaceted reward design pushes the model toward both accuracy and strategic intelligence. The ablation studies in the paper show that each component is essential for optimal performance.
The experiments use the chart mimic dataset for training, expanded with new question-answer pairs generated by Gemini 2.5 Flash. The evaluation benchmarks cover a wide spectrum of visual programmability.
The results show that the adaptive model achieves the highest average accuracy across all benchmarks. It dynamically selects the optimal reasoning path, using code where it's precise and direct reasoning where code would fail.
The comparison with state-of-the-art models is also telling. The adaptive model outperforms all competitors, especially on diverse benchmarks like ChartX and ChartXiv. This demonstrates the power of adaptive reasoning.
The paper also explores scalability. The adaptive framework works well on larger models, achieving the best overall performance on the 32B scale. On smaller models, the performance is more nuanced, but the structured, code-centric reward system still provides a stable learning signal.
The ablation studies dissect the reward function. Without the decision reward, the model defaults to a single strategy, leading to poor performance on certain benchmarks. Without the data accuracy reward, the model becomes overly cautious on programmable charts.
The analysis of numerical fidelity is particularly interesting. There's a direct correlation between the accuracy of extracted numerical data and final answer correctness. High-fidelity extraction leads to high accuracy, confirming the importance of the data accuracy reward.
The qualitative analysis includes case studies that highlight the model's practical intelligence. On a high programmability chart, the adaptive model uses code to extract data and compute the answer, outperforming a standard chain-of-thought model. On a low programmability chart, it avoids code and relies on visual reasoning, avoiding the pitfalls of numerical hallucination.
The discussion and conclusion section of the paper is quite insightful. The authors argue that robust, general-purpose reasoning emerges not from a superior monolithic strategy, but from the metacognitive skill of knowing one's own strengths and limitations.
That's a profound point. The future of AI may lie in systems that don't just follow procedures, but strategically decide how to think. This paper provides a concrete blueprint for building more flexible AI systems.
The broader implications are significant. The framework points toward method fusion, the ability to select and combine different reasoning strategies, even within a single modality. This is a step toward more human-like adaptability.
The authors also discuss limitations and future directions. One area for improvement is moving beyond a binary choice between code and direct reasoning. Future models could perform region-based assessment, applying different strategies to different parts of a complex figure.
Another direction is expanding the vocabulary of formal reasoning. The current model focuses on data analysis logic, but future work could include other formalisms, like signal processing for time series charts or graph-theoretic principles for network diagrams.
The authors also suggest developing self-supervised methods for policy learning, reducing the reliance on annotated training data. This would allow the model to learn the decision boundary by correlating its choice of strategy with final task success.
Looking further ahead, the ultimate goal is dynamic strategy composition. Future systems could synthesize hybrid approaches on the fly, invoking different types of logic for different aspects of a complex visualization.
The path forward is clear. The journey from narrow tools to general intelligence will require architectural innovations that foster cognitive flexibility. This paper is a tangible step in that direction.
Before we wrap up, let's summarize the key contributions of the paper. First, the authors introduce visual programmability, a novel concept for determining if a chart task is suitable for code-based reasoning.
Second, they develop an adaptive framework that learns to choose the optimal reasoning path, trained with a specialized dual reward reinforcement learning system.
Third, their adaptive model demonstrates outstanding performance and generalization, consistently outperforming rigid strategies across diverse benchmarks by intelligently switching between reasoning modes.
In summary, this paper shows that VLMs can be taught not only to reason, but also how to reason, dynamically selecting the optimal reasoning pathway for each task. It's a significant advance in the quest for more flexible and intelligent AI systems.
That's a great summary. Thanks for joining us on this deep dive into visual programmability, a guide for code-as-thought in chart understanding. We hope you found it as fascinating as we did.
Stay tuned for our next episode, where we'll continue exploring the frontiers of AI research. Until then, keep thinking adaptively.
Goodbye, everyone.